Okay, let's get started. Welcome everyone. This is our final seminar of the semester. Once again, we want to thank Lockheed Martin for their sponsorship of the series. Today I want to introduce Dr. Jingjin Yu. He is an assistant professor in computer science at Rutgers. He got his Bachelor of Science at the University of Science and Technology in China. And then he received his Master's of Science in Computer Science and his PhD in Electrical Engineering at Illinois. And he briefly did a stint as a postdoc at MIT, and his work now deals with optimal multi-robot motion planning, and I will let him talk about it. Thank
you. Thanks for the introduction. I'm very pleased to be here to tell you a bit about my research. So let me perhaps start by defining what I kind of do, my core research focus. So my group works on studying kind of these fundamental issues, complexity and algorithmic side of things for optimization problems in robotics. Now, in studying robotics problems, what we want to do is to derive optimal solutions that optimize certain objectives of practical value. For example, in a multi-robot path or motion planning problem, a natural objective could be finding collision-free trajectories while also minimizing the task completion time or the total travel distance. Similarly, in an object rearrangement problem, for example, using a robotic manipulator to arrange these objects on a table, minimizing the task completion time also makes sense. Right? Now, in another setting where we want to generate deployment strategies for a large number of robots or cobots, for example, to guard a barrier or perimeter, it may make sense to minimize the maximum effort taken by any robot or cobot. Now, for studying this, we usually look at fundamental aspects, including things like combinatorial, geometrical, topological, symmetry, and so on. Now, through these studies, we produce results concerning complexity and algorithms. For many of the problems that we studied, it turns out that versions of these problems are often NP-hard or harder. Nevertheless, we still want to find ways of solving these problems, hopefully effectively. Right? And over the years, my group has developed a few of these general methodologies that allow us to attack a wide range of problems. I'll mention a few here. Recently, we presented one of this work on using mixed integer programming as a general method for solving path-based optimization problems that works quite well, generating very optimal solutions very fast. Now, this work was recently presented at IRIS 19 and got 2 Best Paper nominations. In studying task and motion planning problems, we find that we can actually apply dynamic programming very often to reduce the complexity if you are working with some n objects from n factorial to 2 to the n. It turns out that in practice, this actually makes a big difference. We have also developed new divide and conquer methods for dealing with multi-robot motion planning problems. So today I will discuss a subset of these problems and results in a bit more detail. A major direction I've been pushing for the past few years is on collaborative autonomy, which covers subjects like autonomously generating strategies for deployment, task assignment, and multi-robot motion, path and motion planning. Now, I've also been working quite a bit on object rearrangement problems, including settings on Tabletop where you can have a manipulator go grab an object, lift it up, move it somewhere else, and drop it down. We've also looked at a stack rearrangement setting where objects are stored in stacks, and you can only access these objects from the top of the stack. We've also looked at the clutter removal setting. This is also an object rearrangement setting where the goal is to take all these objects from a confined environment out. Again, I want to emphasize that for all these, we want to look at practical optimality objectives. We've also worked with the industry on topics like warehouse automation and recycling automation. So for today, I'll spend the bulk of the time covering topics on collaborative autonomy, and hopefully at the end I'll have a bit of time to cover some of these results that we have on object rearrangement and industrial collaboration. Sorry, got a little bit of cold out there and a little bit of running nose. Okay, so the premise behind our study of collaborative autonomy is really to hopefully eventually enable and improve real-world applications. Right? Today, we actually, in some sense, have a good theoretical grasp, as well as a bunch of computational tools when it comes to dealing with the kind of optimality issues for single robot or single agent systems. Right? Now, for example, if you want to get from point A to point B, you can just put that information into your phone's GPS. Immediately, you'll get an optimal solution out of it that works often very well. However, we cannot say the same for multi-robot or multi-agent systems. While it is true that we have things like these Kiva robots, right, working in warehouses, thousands of them together, or having robots playing soccer against each other, we really don't know, in some sense, how optimal these systems are. That is, can we significantly improve the performance of such systems in practice? And also, can we provide even better, more theoretical guarantees on what is the limit that we can push for? So this motivates my study of collaborative autonomy. As I mentioned, I will cover three kind of topics on motion planning, task assignment, and strategy generation. So how do these things fit together? I'll use a somewhat toyish example to explain this a bit more. So imagine we have a scenario where we want to deploy a bunch of firefighters and robots to kind of monitor maybe a forest area for potential fire spreading. So in this simplified example, we want to deploy these some N robots or human to guard these red perimeter. Right? You can imagine each one of these has certain kind of capacity. That is, they may be able to guard a range of this perimeter. If they do too much work, they will not work very well. Right? If you do too little, then some others will need to do more work. So the first step of solving such a problem is to devise a deployment plan that kind of try to minimize the effort taken by any one of these firefighters or guards. Then after that, we need to match these firefighters with these locations. That is a task assignment problem. And finally, we need to still plan trajectories so that these guards can actually be deployed to these locations. That is, strategy generation, task assignment, and motion planning is a natural kind of three steps in solving this sort of high-level planning task. So I will actually discussing this in a little bit of a reverse order.
Do
Yes?
you assume that you know the locations, and then all these points that you put?
Oh, these locations?
In 3D?
3D?
You have a map? You assume that you have a map?
Right, so I studied this from, we do assume we know this. This is, I only attack this from the point of, I know I want to guard all these perimeters. I just need to figure out how to place things there so that the perimeter is covered. Yeah, I studied this as a more of a computational geometry problem here. Yeah, and we're not solving the vision problem here. Okay. Yeah. So I started studying the multi-robot motion planning problem for quite a few years, and then I looked at a few task assignment problems, and more recently I began to examine strategy generation. Actually, it's a quite rich field with many interesting problems to be studied. So that's how I'll be covering these topics.
Can you assume that the intensity of those fires or the spread rate
No, it's pretty abstract right now. We don't really consider any of these stuff, right? I think actually, I guess eventually I hope to work with different sensing models. Right now it's very abstract. We just assume each, or one of these can cover some range. The more it covers, the worse the quality it will be. That's kind of the assumption, right? Again, this is somewhat new of a new line of work. So first I will discuss the motion planning problem. That actually will form actually one of the bulk of the things that I will discuss today. So we work with the graph-theoretic formulation of the multi-robot path and motion planning problem. One of the reasons behind this is that the continuous setting is simply super hard to deal with. Making it discrete still does not solve all the problems. So we'll work with a graph that is usually connected. And we have a set of robots residing on the vertices of this graph. We call this a start or initial configuration. We want to send them to some goal or final configurations. Now, what we want is that we have a graph, we have some start configuration, some goal configuration. We want to find a set of collision-free paths such that we can move this from this blue to this green locations. Right? Pretty straightforward. In each step, a robot can move from one vertex to a nearby vertex as long as it does not hit other things along the way. Right? So that means there are two things that cannot be done. That is, you cannot have two robots trying to exchange location using the same edge. This is like two cars colliding on a road, right? Or you cannot have two robots going to the same vertex in a single step. But other than these, other moves are kind of valid. So for this basic problem, we examine several common objectives. A most natural one probably is minimizing the max time, also known as the make span. That is the task completion time of the task. We can also try to minimize the total summation of the completion time of individual robots. You can also define distance objectives similarly as these two time objectives. So in practice, of course, this may correspond more to things like fuel usage and so on. In particular, we want to seek optimal or near optimal solutions here. So for most of the things I try to deal with, whenever possible, I want to find the true optimal solution. This is in some sense slightly different from the computer science theory people who sometimes care more about constant factor and so on. I do study some of these things sometimes as well. So ideally, that's one point X in practice. Okay, so now once we have this problem defined, if we don't want to optimize this problem, it turns out that the problem is actually easy to solve. That is, if you don't care about optimality, you just want to find a feasible solution that routes all these robots. You can do that in cubic amount of time with respect to size of the graph. However, once you want to deal with this problem optimally, solve it optimally, it becomes immediately NP-hard. So here I will show, I think, a quite cool kind of reduction showing that the minimum make span multi-robot path planning is NP-hard. So we reduce from a standard 3-set problem. Here we have a 3-set problem with 4 variables, x1 through x4, and 3 clauses. So n is the number of variables, m is the number of clauses. So we'll be building a multi-robot path planning problem as follows. For each variable, we build a gadget that looks like this. It has an upper channel and a lower channel. Each one of these channels is of length m plus 2. So we place a robot on the left side and ask this robot to go to the right side. So this is the start, this is the goal. Now you can easily see that every robot must travel m plus 2 steps to go from left to right. And then for each one of the clauses, we create something like this. For clause 1, which corresponds to x1, negative x3, and x4, we place a robot here. We connect this to the upper channel of x1. lower channel of x3, upper channel of x4, and we want this to eventually go here. We do the same for this second clause and the third clause, just shift one to the right. So we create a situation where we want to route all these robots to this side, but all these robots to this side. This causes complexity. We can show that actually fairly straightforward, that if the three-set instance is satisfiable if and only if this problem has a mixed span of n plus 2. So I'm showing this because I think this is one of, when you do this kind of NP-Hardness proof, often it's kind of quite complex. In this case, it turns out to be quite kind of straightforward to show. We can actually also prove the same for all the other objectives. That is, if you want to minimize mixed span, total time, min-max distance, or mean total distance, they are all hard, but the other proofs are kind of more involved. So briefly, we mentioned that we could also actually establish similar results when we restrict the graph to a planar graph. So for those of you who are not familiar, planar graphs are graphs that you can embed in the plane without edge crossings. Right? The additional significance is that such graphs kind of mimics our road networks, right, which is kind of mostly planar. So this connects us to a little bit kind of a practice. That is, in some sense, planar multi-route path planning being NP-hard to optimize sort of implies if you want to optimally route traffic, it's also hard. Of course, this is, I didn't use imply, I used quote unquote, right? So it's not an exact implication. So that perhaps suggests that we should not try to find optimal traffic routing algorithms for a large number of cars and so on, and still hope to be able to do this efficiently. Perhaps instead we should try polynomial time suboptimal solutions, or we could try fast methods with some good solution quality, but not optimal. Right? On the other hand, you can also try to engineering the environment, which is something we've already done. That is, you change the underlying graph or road network. So we have things like, instead of one-way road, we always have like often two-way roads whenever possible. Also multiple lanes. That helps alleviate kind of traffic problem. Although they never really work in the end because people just keep driving more and more, I guess. And you can also have things like elevated intersections, that is overpass, to help with this kind of settings. So for me, I will actually focus on the algorithmic aspect. So I'll introduce some polynomial time suboptimal solutions and also some fast methods with good quality guarantees. This next work is something I did on my own and presented at RSS 18, where we actually solve a really constrained problem. We're working with a grid graph. So this can be arbitrary large grid. We want to route all these robots. Each vertex has a robot on it. We want to route them from arbitrary initial configuration to a row major ordered final configuration. This, of course, means that you can go from any arbitrary start configuration to any go configuration. So first, let me state the result. In an arbitrary fixed dimension, so here we show a grid. It's like a 2D grid. Our method actually works on arbitrary fixed dimension. So if you have like 3-dimension, 4-dimension, 5-dimension grid, all this would be fine. We can actually compute a constant factor mixed span optimal solution in quadratic amount of time. That is, if you have v vertices here, it takes only this much time, OV squared amount of time, to route from any start to any go configuration. So our method uses two kind of subroutines that we developed. We call this SAG, standing for split and group, and PF, standing for partition and flow. So I'll be quite brief in terms of covering these methods. First on SAG. So when we are given a grid of size ML times MS, we want to go from this to that and solve that with SAG. SAG can solve this problem, but will not give us the constant factor optimal solution. What we do is, with SAG, we split the grid in the middle along a longer dimension, And this split induces a split of the robots themselves into two groups. That is, some of the robots, as you can imagine, right, needs to go to the right side eventually. Some of the robots need to go to the left side eventually. So in this case, all the you can check this, right? All the orange ones should go to the left side and right side eventually. All the purple ones should go to the left side eventually. We want to, after this split, group these robots based on where they should be in the end. So that's why we call this split and group. Now, if we can do the first step, that is go from this to that, in this much time, in this many kind of time steps, right? That is OML plus OMS. Then we can apply this recursively. Now the second time we are applying to this one and this one in parallel. That will take this much time. And then we can again cut it, apply to 4 of these in parallel. We get that in this much time. So it turns out if you add all these up, you end up with the same asymptotic complexity. That is, if we can do the first step, we can actually solve the problem using the same amount. Yeah.
Maybe I don't understand something, but shouldn't you have an empty space, an empty node? How are they going to move?
So we can rotate. We can rotate.
Eh?
We can rotate.
Or they can all move
Yeah. They can all move.
all together.
They can all move together as long as you provide a non-intersecting cycle. They can move along the cycle.
But you could, in principle, have empty spaces also.
Yes. Yeah. Empty space, of course,
And
you
the
can.
algorithms will change.
With,
Because you could be moving, like, there's this game.
yeah.
Right?
Yeah.
You move, but you need an empty space to
Right.
start moving.
For that one, it's like because that one has very tight interlock. Right. Here, we do assume that you can, for example, do things like this.
Okay.
Yeah. That's in the original.
So you can do any rotations
Correct. Yeah.
for any square.
For any square. Yes.
Okay.
Yes. Yeah. Okay. So we'll show how actually we can kind of do this. Okay. So we'll need some kind of motion primitives, as we kind of do with almost any robotic planning sort of problem. The first one is a constant time step edge flip on a very small grid. So if we have a 2 times 3 grid like this, we want to flip 2 and 3 without changing others kind of robot's location. What we can do is we first do this rotation, followed by this rotation, and then followed by this rotation. Finally, we get this configuration. As you can see, 2 and 3 are flipped. All the others remain where they are. Now, once we have this, it turns out that we can do multiple of these in parallel. Like in such a setting, right? If we want to flip all these, we can put them into their individual 2 by 3 grid and do all these things in parallel and flip all of them. So we can get this again using constant number of times. In this case, of course, it's like 3 steps. In this case, again, you can do this in 3 steps. So from there, we can actually get a higher level motion primitive. That is, we can exchange 2 groups of robots, this purple and this orange, on a length L path using only OL steps. Of course, we assume this one is embedded in a grid. That's when we can do it. So you can go from this to that using this many steps. Okay, from there we can actually get to the task we want to accomplish. That is this thing. What we do is, now the details how we can generate this kind of desired exchanges is put in the paper. This one will take like additional quite a few slides to explain, so I'm not going to get into that part. So we do a bunch of these vertical exchanges using the previous primitive. We get a configuration that looks like this. After that, we do a bunch of horizontal exchanges between these 2 groups. And then that is followed by another vertical exchange. Now, at this point, we get to a configuration that looks like this, where for each row here, the number of orange robots is the same on the left side, the same as the number of purple robots on the right side. Now at this time, we can do a final exchange to reach this using again the same primitive. So we're applying the previous OL time primitive 1, 2, 3, 4 times all in parallel to actually go from this to that. So that is the entirety of the split and group algorithm. And I just want to mention here, we can actually do this, of course, for higher dimensions. Now with that, we can construct the whole algorithm called partition flow. So I'm just going to be, again, very brief here. First, we need to compute something we call DG. That is, for each robot, we compute the distance, Manhattan distance, from its start to its goal on that grid. Right? And we take the max of that. And based on that, we partition the larger grid into small cells of roughly the size dg times dg. With this partition, we have the property that for any given robot, it must have its goal either in here or in a nearby cell. This is just by definition of that dg there. What that also means is that because all this, we have this entire thing filled with robots, right? If some robot needs to go out of a cell to reach its goal, that means some other robot must also go in that cell to fill the hole there. So that allows us to construct a flow of these robots. And after we execute this flow, it ends up happening that every robot must be in a cell where its goal must also be. And then at that point, we can again apply the SEG algorithm previously to solve this problem. So in the end, we end up with a make span of ODG, which is what we want. Okay, so this is again what we have mentioned before. So of course, at this point, right, some of you probably already kind of be laughing a little bit because, you know, as we do with this sort of thing, we know that here is O1, right? It sounds very nice, constant factor optimal. But here the constant is often quite big, right? We actually did some evaluation. For us, it's around some 40, 50-ish. So yeah, it's constant factor, but it's a huge constant factor. It's like if the optimal solution takes one step, this one will take like 40 steps, right? So it's not actually quite ideal. Of course, in terms of theoretical guarantees, this is quite nice to have. So we also try to solve this problem near optimally. That is, we want to also solve this in a one-point x optimal. For this, we used a method via integer programming. That is part of the general method that we presented at this IROS. So what we did was we transformed the multi-robot path planning problem to a multi-commodity flow problem over multiple steps. That is, roughly, what we do is we take the original graph, we make a bunch of copies of this and train them over time. So each of this edge, which is carefully constructed, represent a binary variable. If an edge is used, it means, if an edge is set to 1, it means it's used by a robot to go through that edge at that time. If the variable is 0, it means that edge is not used at that time. Right? So eventually, if we do this, if we kind of try to solve this, we'll end up having a set of zeros and ones that gives us the solution. Of course, we need to incorporate the collision avoidance constraint that I mentioned when I defined the problem. So due to time, I'm not going to go to the details. But once you do all these things, you get an integer programming model that you can shift to a good solver, and it will just give you solution. Turns out this model is quite efficient. So for example, we can solve problems like this, where we have a bunch of randomly generated start and go configurations on grid with a bunch of things kind of carved out to represent obstacles. So if we don't add any additional kind of heuristics where we want to find the exact optimal solution, we can actually do this for that previous 24 by 18 grid for up to about 100 robots. And we can compute these in under about 100 seconds for most of these. So here, the varying is a different kind of number of vertices that are removed to represent obstacles. So if we add some additional heuristics, which I'm not going to kind of describe in detail here, we sacrifice a little bit on optimality. So here, this is true optimal solution. Here, we're showing the optimality ratio that's conservatively estimated conservatively. We basically take the shortest possible, which we might not actually realize, and we use that as the baseline. And here we can see that for most of these, we can actually hit 1.0 some optimal for majority of these. So this is actually basically same as kind of optimal solution. In practice, I mean. Now, we can actually do this for up to about 180 robots on a fairly kind of small grid. And this can be done for most of these in under 10 seconds. So I just mentioned that here we have about 44% of the grid cells occupied by robots, whereas the settings like this, the occupancy is only 15%. So 44% is just very, very full. Okay, so it turns out that the method is also very effective as a means for finding an initial set of optimal or near optimal solutions for solving continuous problems. We have used this ourselves to attack this two-dimensional kind of routing of a lot of robots in continuous domain. And we actually have people picking up our work from USC and MIT. USC, they used our methods as a baseline method for coordinating a bunch of drones. And MIT, they did something quite interesting. They have this kind of small quadcopters. They added some wheels to it, so it can both fly and actually go on the ground, representing kind of some hybrid vehicle. They also used our method to plan the initial trajectory. Okay, so moving on to the task assignment problem. Given the time that I have, I'll only illustrate kind of two results here, one per kind of slide. One is on a discrete setting, and one is on the continuous setting. Okay. So in the original kind of multi-robot path planning problem, right, we have all these robots kind of labeled. We know one must go there, two must go there, and so on. Now, what if we could remove a label? Now, I've done a survey at some point. I asked like a bunch of people, right, or kind of PhD students or professors, right? So roughly half of them think this problem is harder. After all, it seems like you have to first, again, give these things labels, right? And then you still need to plan trajectories for them. As it turns out, this problem is actually easier. It turns out the flexibility in labeling actually allows us to avoid collision. I'm not going to go to the detail. I'm just going to mention the result here. That is, we can actually compute very efficiently a distance optimal solution. And moreover, we can execute this solution even in a distributed manner. That is, once you plan the initial trajectory, you can ask all the robots to just execute this using only local communication. Now, I should mention, of course, other groups like Vijay Kumar's group at around the same time also developed some similar method. So this is one of the animations that I prepared when I was still at the University of Illinois going to MIT to do a postdoc. This was something I prepared for my interview there. We have like about 140 kind of robots moving from two kind of formations. And we can do a planning like this. For this particular problem, I think it takes about 0.01 second to run on a computer like my laptop. Okay, so now we have kind of dealt with the unlabeled version, right? What if we further remove the underlying graph? That is, we have some initial configuration of the robots. We just want to send them there. This obviously is a little bit difficult. We could still, in this case, in low polynomial time, under some mild clearance kind of assumptions, that is, the robot cannot be too close with each other and so to compute something that's almost optimal, we can compute a solution with OPT plus some for n, where n is the number of robots. Here we assume each robot is a unit disk. So this is a distance that we need to potentially actual distance that we need to travel. So it's a kind of near optimal solution. And we can solve problems like all these very efficiently. For example, routing all these things here, this here, the blue ones to the red ones, and so on. So that's all I'm going to say about the task assignment. And moving on to strategy generation. This last topic is something I picked up more recently in the last year or so. But I found this to be actually quite interesting. I think our plan is to actually study this for the next at least 2-3 years, I believe. There are many interesting actually problems coming out of this. But for today, I will kind of mention a little bit of the background behind our study and some kind of more of the preliminary results. So there are many kind of problems people have studied in the past involving kind of generating of deployment strategies. Now from the control side, these are often done as a sort of consensus problem. For example, we could be doing this sort of rendezvous. That is, we want to get a bunch of agents to kind of converge to some unspecified location. It could be that we want to move the robots, right, to get a good coverage based on some distribution. So from one distribution, initially robots are like this, then you want to kind of cover this more important areas. It could also be trying to do the kind of consensus in phase space. For example, you might want to reach the same kind of heading, right, or same kind of velocity. And then from the computer science side, these problems are often kind of studied as an explicit optimization problem versus it's often done in the control side as implicit and iterative solutions. So this, a prime example here is the art gallery problems, where the general goal is to kind of find a location of a bunch of guards, right, so that every point in this kind of polygon is visible from at least one guard. And these studies generally, again, they produce something like O1 optimal. They don't really try to find one point X optimal solutions. Also, they generally work with this sort of infinite kind of visibility assumptions. So this motivates us to kind of deal with more practical settings. And we started this line of study with the optimal perimeter guarding problem. Again, I want to say we don't solve any vision problems. We're really working with a kind of quite abstract model here for the moment. We are working toward more and more realistic and realistic and 2D and sensing models. So here, I want to define the problem because it's kind of relatively kind of new problem. We're to guard, in some sense, a 2D region. So everything here inside here. We want to guard a perimeter of this region. That is here, this P is this S1, S2, S3. And this leaves us a bunch of so-called gaps, G1, G2, G3. That is, there are certain important part of the boundary that we might want to guard. But there are certain part of the boundary maybe we just don't care. So we're given some N guards, maybe human or robots. What we want is a set of segments. We want to divide, in some sense, the entire boundary into segments. For this case, we have N equals 8. That it would have 8 of these segments. We want such that the union of these segments would cover all of P. We don't care if it covers any of these gaps or not. It can or it does not need to. So we want to essentially minimize the maximum guard effort. That is, we want to find such a coverage such that the max of this length is minimized. That represents basically we don't want any guard to do unnecessary work, more work than the others in some sense. We can generalize this to support multiple perimeters. Here is a single perimeter. And we're also working with heterogeneous guard types. For example, you might want to have a human robot team to deal with this, or different robot types. And right now we are also working on more complex sensing and sensing models and complex domains. Okay, so now I don't think I will have enough time to cover the solutions. So I'm going to only mention a property that's kind of important to say so that things make sense, right? One of the most important properties is that covering gaps may be necessary. It helps in some sense minimize the actual maximum length. So look at this example, right? We have two segments, S1 and S2. Now if we have two guards, then the optimal solution would look like this, where the coverage of guard 1 would actually span over this first gap. So this means sometimes even the gap, you don't need to cover it. It's actually beneficial to kind of cover it. So I'm not going to actually talk too much about the rest here. I'm just going to jump directly to the algorithm part. So we can derive, based on this a bunch of properties that from the previous page, we can actually derive a naive algorithm that runs in n squared and q cubed, where n is the number of guards, q is the number of segments on the boundary, and with the application of two bisection, which requires quite a bit of reasoning, we can drop that to q squared log n plus q. This is actually very fast. It can be run on like even a billion robots without any problem. So here are some example kind of simulations, right? I'm going to only point out maybe this one here. You can have, in this case, two segments, two red segments. So q equals 2 and n equals to 5. So this is the perimeter. This is the coverage. We actually have 5 robots covering like this. That actually covers this gap. Okay, so from the baseline formulation, right, we can do kind of many generalizations. We can do this for multiple parameters. We can use the same technique and maintain the efficiency. Of course, we can also combine this with task assignment and motion planning to solve a more complete kind of task. And more recently, we have also had result on heterogeneous guard types. As it turns out, it becomes actually immediately harder. For example, we could have k types of robots with different capacities. For example, a type I robot can cover some length Li, and with the cost of Ci. So the goal is to cover the thing with the minimum amount of total cost. Right? This would be a natural thing to do. It turns out that once we try to do that and make k a variable, the problem becomes actually strongly NP-hard. On the other hand, if we fix this k to be a constant, we can again apply something like dynamic programming to get a pseudo polynomial time algorithm that works actually quite well in practice if you have k being 2 and 3. K being 2 is actually useful, that is if you have a human robot team. We have many active research threads unfolding here as of now, and we're also working on hardware experiments. So this concludes the collaborative autonomy part of my talk. Next, I will kind of provide some highlights of the other projects that I mentioned. Let me see, how many time? I guess probably will be another 5-10 minutes. So as I mentioned in the beginning, we're working on this optimal tabletop rearrangement, object rearrangement problem, where we want to move a set of objects from some initial configuration to some goal configuration by lifting one, move it somewhere, and drop it down, and eventually go from one configuration to another configuration. I mean, these things has quite a few kind of applications. For example, if you want to tidy in a desk, as we're doing here, or in an industrial setting, you want to pack things and so on. So we want to minimize, of course, the task completion time. As reflected here, It's the number of grasps that you have to do, plus the end-effector travel time. Now, the complexity here are twofold. First of all, for example, if you want to move the sprite to here, the Coke can is in place, and they will block this. If you want to move the Coke can first to here, again the sprite can will be blocking it. So this creates this circular dependency. What that means is that if you want to solve this problem, you have to lift one of this and put it somewhere else, right? This increases the number of grasps you have to do. As it turns out, this problem is equivalent to a well-known hard problem called feedback vertex set problem. And this problem is actually very, very hard to solve, even for very, very small instances. And after you kind of untangle all these kind of dependencies, you are still left with another kind of hard problem, that is the traveling salesman problem, for your end effector to move around. So what we end up doing is that we eventually used again, an integer programming-based method for solving this problem that scales to roughly about 20 to 30 objects, which is of practical importance. So here is one example where we run our algorithm versus a kind of greedy algorithm. So it takes about 300 seconds for us to execute the plan, and about actually 400 seconds if you use a greedy method. Okay, so a second topic I'm going to discuss a little bit is on optimal stack rearrangement problem. So here, objects are placed in stacks, and they can only be accessed from the top of the stack. Again, we want to arrange these objects in some manner, say from that to that. Okay? I apologize if some of you are colorblind. Lots of my stuff have colors in it, and sometimes people feel a little bit frustrated. So we want to minimize the number of stack, pop, and push kind of operations. This is essentially kind of like stacks in computer science, right? We can only grab it from the top, move it to another one, and then do things like that. Okay, so it actually has some practical relevance, right? For example, at this shipping ports, you have this kind of container carriers. They actually kind of move containers in a similar way. These are essentially stored like stacks. You can only kind of move the top one and so on. So for this problem, we show that if you only want to do this kind of sorting of types, you can do this in O and D log n push pop. That is, D is the depth, N is the number of columns. And if you want to do so-called full sorting, that is, instead of having only colors, we further give labels 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? That's a little bit more complex. We can do this in O and D log n plus log D push pops. The lower bound here is omega and D, which can be easily established. We also derived some search-based near-optimal algorithm for solving this problem that scales again to about 20, 30 objects. So here's an illustration of a simulation where we did to use a KUKA U-boat to rearrange a bunch of soda cans. So more recently, with my collaborator, we were able to actually push that limit, the upper bound, to O and D. That is, it meets the lower bound for almost all N and D. There's a small set we're still kind of working on. We think we probably cannot get that to actually N D. So we're probably also trying to kind of make this upper bound a little bit higher. So I will also mention very briefly the optimal clutter problem clutter removal problem that we're working on. Right now we have done the kind of single robot case where we want to essentially use a robot to clear clutter from an environment. The general goal is to remove all of these things and minimizing the task completion time. So we can also show the problem is hard in extreme cases. So in practice, we can actually use dynamic programming, again here, to solve problems to up about 40 objects in around 50 to 100 seconds. And interestingly, clutter actually in some sense helps, because as you try to solve this problem, in some sense, objects on the outside actually blocks you from accessing objects from the inside. That actually reduces the search space. It turns out that somewhat to our dislike is that a greedy approach actually works well in this case as well, almost as well as optimal solutions, because as you scatter the object randomly, it turns out that whatever you do does not matter as much. We can also work with multiple exits and so on. So last, we have done some collaborations with industry. One of this is something we did with JD to help them with some product packing work, where we actually managed to get this thing published at ICRA and get some award nominations for it. The goal here is to try to pack things as tight as possible from the initial kind of cluttered setting into a kind of organized setting. Another more recent project I'm working with, a recycling company, is try to help them automate their product kind of lines. They have many different things they do. For example, they pulverize a bunch of condensers and get a bunch of coppers and aluminum, and they want to separate them. Some of them are easy to do, and some of them are hard, because once you have aluminum wrapped around the copper, it's very hard to separate them mechanically. So we kind of use both computer vision and some manipulation to do things like this, which I think is quite cute. We're still in kind of early stages in doing this, using kind of a tool to help us kind of declutter and do picking.
You should work on your spreading algorithm.
Yes, so this is still early, but this is very hard because these are irregular shapes, right? You cannot actually easily run this in simulation, unfortunately. If you use we tried some physical engine. It seems it does not really give us what we want. At least we don't know how yet to set the parameters so that it would translate to real settings. So have to right now be doing this in a more like ad hoc sort of manner. Yeah, it would be good to know how to do this more effectively. Okay. So that concludes my talk. So here are the people that the papers that I mentioned involving all these people here. There are some of my students, some of my advisors and the collaborators, and so on. Thank you. Happy to answer any question I might have.
Can you go back to that video where you are changing the objects from one location to another on the tabletop?
This one?
Yeah, that one. So here is an algorithm which is probably more efficient than that, but it's more cognitive. So what you do is you take them out.
Yeah.
And then you pick and put in the final location.
Yeah, of course. Yeah, you can definitely do that. So in certain cases you can do this. Certain cases you probably won't be able to. It's for humans. It's actually, I would say, very easy, right?
Yeah. I really like your approach of dealing with objects on the table. This is something we are also working on.
Okay. Yeah.
I think it's a big part of the future of robotics.
Yeah.
Like putting things inside boxes,
Yes.
That.
Yeah.
But I have another question for you, which is more fundamental.
Right.
You showed the interactability of a number of plugin problems, an assignment problem.
Right.
NP-Hard,
Yeah.
20 years ago, about 25, theoreticians and vision people, they got into the habit of proving NP-Hard problems. So it turns out, like almost any interesting vision problem, is NP-Hard.
Of course, yeah.
but we solve them.
Yeah.
So what I want to ask you,
Right.
so those proofs, they were very interesting, of course. Like your proof, I really liked your proof with all the
Yeah. Thanks.
satisfiability.
Yeah.
But what influence did they have in the field?
Well, so
So those proofs, what influence do you expect to have in the flying field?
for one thing, right, so this is kind of not completely related, I guess, to what you're asking. Is that people likes to cite this sort of hardness proof to justify what they do. That's one thing I found out. Right, I actually the proof that I presented turns out to be my most highly cited work on so far. People all say, "Oh, this problem is hard, so we can do this, and that."
That's because of the reduction. The reduction is a very interesting one.
Yeah, thanks. Yeah, so I mean, I don't. My goal is actually not to. I think I also insinuated when I first talked about things I do. Right. I think what I said is, I do kind of do this sort of stuff, but despite this hardness, we still want to find effective method for solving them. So my goal is actually not to just show problem is hard. Regardless of the hardness, the eventual goal is to design algorithm for solving this. And some of these are difficult in the sense that we are dealing with, for example, this kind of problem, right? This rearrangement problem. If you really have to do this kind of disentangle of the dependency, I don't actually believe there are other ways for dealing with it. So it's just a hard problem. There are certain problems that are just hard, but there are certain problems that are not as much, right? For example, problems like this, you can easily generate some sort of solution, right? Then the rest is how good it is. You can, yeah. So yeah, I think not all of these problems are the same. Some problems are just naturally hopeless, right? I think there are also problems in vision like that, right? And then some of the problems we hopefully will gradually be able to solve them. For example, I mentioned many times that some of our algorithms can deal with some 20 objects. This actually put it into the practical bucket now, right? You don't need to work for your algorithm to work with 1,000,000 objects. You don't need to do that to call this algorithm efficient, right? If I want to clear something on the table or arrange things on the table, if I can work with 20 objects, I think I solve most of practical cases, right? So I hope to kind of produce algorithms that solves practical problems, and then hopefully with better and better computer we can solve. Yeah.
I also had one idea that you can discuss with your colleague El Gamal, who is our graduate.
Oh, okay.
As you were explaining the algorithm, where you do the rotations so that you can change everything.
Right.
You can imagine that you have people on a stage, and the people are the disks, and they start walking around.
Okay. Yeah.
In squares and circles and in parallel, and they start randomly, and then at the end, maybe they spell something,
Yeah. Okay. Yeah.
Together with the dance department.
I think actually
a new kind of art.
I think there's this person at Princeton. I don't recall her name. I think at the mechanical engineering department. I think she did something.
El Gamal is doing art now.
Yeah. Sure.
Well, that's what he likes.
Yeah.
So you can do some cool art with this algorithm as it's running.
Yeah.
The people will have to, of course, remember.
Of course. Yeah. So.
But that will be the dance.
Yeah. So I think so this is something actually we kind of do. I guess. Moon is not here, right? So for example, people do this with drones and stuff like that. Certainly you can do this with people. Yeah, I think it certainly is interesting kind of direction to go. Probably working with someone in that domain to make this.
For drones, for advertisements, for example, where you can have various.
Although I'm already annoyed when I sometimes see the planes drag some flag and in the air. I don't know if you get a bunch of drones in the air.
In those situations, those graphs that you refer to, this M can get very large.
Yeah.
But in a real practical situation, when you have a robot that is going through a building and it's going to go out,
it's not a problem, yeah.
Then these ends are not very large.
Right, right. So these are meant for things like warehouses, right, where you have lots of these robots. So for example, Kiva systems, they now have, in a single warehouse, they can run 4,000 robots together, all in a single warehouse. So it's pretty, yeah, many of these. And they are actually interested in improving 1%, 2%, efficiency, right?
Of course.
Yeah, yeah.
On the question about the motion planning, you said that the space is n-dimensional. So you have studied this problem in dimensions higher than 2.
Yeah, yeah.
The assumptions you're making in the d equals 2 case are that it's a planar graph, and all your rotations are in that dimension.
Yeah.
You showed an example where there's a one-dimensional rotations embedded in that.
Right,
So
right,
I'm wondering,
right.
what are the assumptions when you go to higher dimensions? Are you always doing rotations in the dimensionality of the n-dimensional planar graph?
Yeah, well, I'm always doing it in 2 dimensions. I'm always doing it in 2 dimensions.
Rotations are in higher dimensions?
The rotation also is always in 2 dimensions. I basically do this iteratively. It turns out that, unfortunately, I mean, the work is like some 30 pages. I condense it too much, right? It turns out that it's not in some sense a super smart way of doing this, but as you deal with these high dimensions, because we are characterizing our complexity in terms of number of vertices, as you go higher and higher dimension, the actual length of each dimension actually goes smaller and smaller. So all this, if you do this kind of 2-dimensional things many times, you don't actually occur a lot of cost in doing so. So we're just doing things always like this. Basically, so first, so in 3 dimensions, what we do is the following. We basically do this in a bunch of planes. Then we do a bunch of things over this like this. Then we do a bunch of things like this. Right? So it's always happening in 2 dimensions. Yeah. But you can partition this into many layers. Yeah. Yeah, sure.
Yeah, so I had a question about the the general framework for the optimization problem, where you have this problem that you're splitting up into deployment strategy, task assignment, and motion planning. So for the strategy generation, you're sort of considering a cost function that is effort, guardian effort, for example, for the perimeter patrol.
Right.
But then for the task assignment and motion planning, it's like distance of how far the
Right. Yeah. So yeah, I see what you mean. I think I can answer your question from here, right? I'm studying this kind of things as somewhat a separate problem. I'm not saying kind of solving as a single problem.
So, but I think all 3 of the problems are kind of solved using integer programming methods potentially.
So some of these things, integer programming method, it's okay when you try to deal with something with a discrete element in it. But when it goes to certain continuous domains, it becomes a little bit hard to encode this very well. I am playing with this for sure. I'm trying to solve in some of this, right? I don't have a exact answer to this. Sometimes we find combinatorial methods are easier. I mean, what I mean easier is like more efficient. And if you can have a combinatorial method, definitely go for that, right? That's what we always try to. First try to see whether we have a good combinatorial algorithm for solving it. And if not, then that's like a backup, right? You can almost always get something with it, right? Yeah.
So in terms of application, you talk a lot about warehouses, You're deploying, you say 4,000 robots, Kiva?
Yeah, 4,000. That's what I heard. I talked to Joey, and he said like they have 4,000 in a single warehouse. Some of the warehouses they are actually more than 1 floor. They have 2-floor warehouses, right?
Besides the warehouse, which is a huge application, anywhere else you think there being multi-robot systems are close to being deployed?
Yeah, lots of places, right? For example, now these are actually at the port, the shipping port. I think this is Los Angeles. These are like carrying this basically containers. These are all.
It's kind of like a warehouse, right?
Yeah, it's like a warehouse.
Open road setting.
Oh, okay. I did not include all these things here. I mean, there are certain things that you can do. For example, one of the things that I found out is that there are this kind of microfluidic chips, where you can manipulate this micro droplet right on this to kind of by doing like static charge, they kind of move on this. They're almost like robots, and what they do is they can use this to do kind of large-scale bio and chemical experiments, right? And again, here you can do routing of these things, and if you do this more efficiently, more compactly, that will also have a positive impact. There are quite a few different places where these things can be actually applied.
See more application,
It's quite interesting. I mean, one of the kind of plan that I have, going next is actually to drive the application side more. Right? Yeah. And I also want to support more realistic kind of robots, differential constraints, all this stuff. Right? I want to kind of be able to do this. Oh, yeah, okay.
So in reorienting the cans, you had an empty space, right? Like,
Yeah.
but like when you do the problem of separating orange squares and the purple squares, you always went with the square.
Okay, in that case, you're confined in that. Yeah, you're confined.
So
Yes.
would an empty space, like either in both directions, would it help your optimality? Like when
Actually, in terms of the, you cannot do better than constant factor optimal, right? We already showed this is constant factor. In a sense, in that sense, it's the best possible. But of course, in practice, you can always drop that constant to be smaller and smaller and smaller if you have more empty space, right? For example, if you just ask some people if you run a bunch of robots on a football field, for example, right? You don't even need to consider collision at all. You just this go here, this go here. Most likely, they will not collide, right? Yeah.
Thank you.
Thanks.